All right, we're looking at exponential models here, and this is just a kind of differential equation. And specifically, we're talking about kind of the interesting solutions that come from types of differential equations. So exponential models are ones where the rate of change is proportional to the function itself. Or, if we're looking at something changing, it's changing at a rate compared to how much is there. And so this is most often seen with populations that reproduce, or if you have finance and you have like a bank account that's getting interest based on how much money is there. These are called exponential functions because the solutions are exponential functions. So, it tracks kind of logically here. So here's an example. Find the particular solution for the initial value problem of g prime of x equals 7 g of x, where g of 0 equals 5. So we've got a differential equation here, dg by dx is equal to 7g. So this is a separable differential equation. I can rewrite this so that they're separate. So 1 over g dg is equal to 7 dx. Integrate both sides, and I get ln of g is equal to 7x dx 7x plus c. E to the ln absolute value of g is equal to e to the 7x times e to the c. And I get g is equal to c e to the 7x. Because e to the c can be written as c. So now g of 0 equals 5. I say 5 is equal to c e to the 7 times 0. E to the 0 is just 1. So c is equal to 5. So g is equal to 5e to the 7x. And you see it's an exponential function. It has e to the x power. So that's how these will typically look. Let's do another example that's shows a bit more of like a real world example. The value of a certain investment increases at a rate that is roughly proportional at any time to the balance at that time. So we say that dp, and this is just because we use in finance, you'll see it p for principal, but this is just the amount of money there. And if it's roughly proportional to the balance at any time, well, it's going to be proportional to how much is there. So dp equals e, dp dt equals kp. And then they give us a bunch of values here. So let's solve that differential equation first. dp by dt equals k. Again, a proportionality constant times p. And that will give me 1 over p dp is equal to k dt, just algebraically rearranging. Ln of p is equal to kt plus c. P is equal to e to the kt times e to the c. This gives us p equals e to the kt times c. So p equals c e to the kt. If you've done in math, you might have seen this as p equals the initial principal e to the rt. That's where this equation comes from. It's just saying that at any point in time, you're changing how much you have based on the proportionality, or based on how much you have times some constant. Anyway, coming down here, we know that p of 0 is equal to 1600, and I know that p of 365 is equal to 1920, and I want P of 90. So we need to find the C and the K. So we're just going to start plugging in values here. So 1600 is equal to P0, so CE to the K times 0. This will be 1. So that means C equals 1600. And that's where you see, oh, this is, if you're used to economics or kind of the continuous compounding interest, we see why this should be the initial value, whatever you started at. So now I know that P is equal to 1600 e to the kt. And now I know that P of 365 is 1920 is equal to 1600 e to the k times 365. 1920 over 1600, the natural log of that will equal the natural log will equal k times 365 times the natural log of e, which is 1. This gives us a k value of ln, I didn't actually solve it, ln 1920 over 1600 divided by 365. And I'll leave it then as an exercise for you. You can take this, and you can actually calculate what that number is, plug it in here. And then for P of 90, you just have to plug in T equals 90. If you have questions, feel free to ask, but that'll kind of wrap us up here.